麻省理工学院的气象教授 Lawrence， 那个学校就在波士顿的城。这也是坐标原点，到时候可以看到坐标原点放在那儿了。你看，你们能听到一些没有？噪声比较高。这种吸因子它是有便利性质的，那是过渡过程。这也是，就是周围那个框上那些值作为初值。这当然不是一条轨道，很多条轨道了。同样的问题，换个角度看。就是刚才在那儿有170个粒子挨着在一条线上，过一会儿它就全散开了，所谓的初值的敏感性。
sensitivity with respect to fluctuations of initial conditions and the mixing property has the effect that, in spite of strict determinism, their movements are practically unpredictable. The movement here is reminiscent of the eruption of lava masses. Two experiments, we look at how the Lorentz attractor is established by the Lorentz equations. The Lorentz equations are indeed based on parameters. We now vary one of the parameters r between the values of 1 and 28. We first examine the stability of the stationary points.
这是一个不动点，那个头上有两个不动点。参数小于28的时候，这个不动点是稳定的，那是个不稳定的双曲点，你可以看到。 接近双极点的速度很慢。这是一条同速轨道，以那个不稳定不动点。把一个3维的轨道变成一个1维的影射，每次只把 z 轴的最高点记录下来，然后把 zn-1 和 zn 标在这个图上，这种所谓 first return map， 那边慢慢形成这个 zn 到 zn-1 的影射。等那影射完全出来以后，你可以看到，靠1维影射的知识，你就知道这里一定有混沌运动了。这样的一个差不多很陡的人字影射，每一点的导数都是超过1的，都是不稳定轨道。但是这个影射只能说明有混沌，没有反映它的对称性。 在产生这个片子的时候，对于罗伦兹模型中的周期轨道知道的还不够多。他给大家看的是最早1到30， 24到28就逐渐出现混沌了。这是下一个电影的头。实际上这个 R 比方说从1变到350，中间会出现很多周期窗口。那这些周期窗口的符号动力学等等，现在当然是完全清楚，文章到了1998才发出来。这个片子大概是在80年代后期做的。IWF 是德文的科学电影的研究所。这儿呢 Wissenschaft Film 哥廷根的。这给大家看一个副摆，就是比简单版要复杂一点。双摆，一个单摆是不会出现混沌的，如果不加以别的驱动等等，但是一个双摆就可以了，它的自由度高。
Look carefully here at the way the outer pendulum sometimes rotates through and sometimes swings back. Over and over again it is forced to decide between these two alternatives, and its choices are by no means regular. Clearly, small differences in the initial conditions have major consequences later on. See two double pendulums starting under almost identical initial conditions. For a while, their traces can hardly be distinguished. Then suddenly, their ways part. At the top, the outer pendulum chooses to swing back, while at the bottom, it rotates through. From now on, there is hardly any similarity between their motions. Let us repeat the critical phase. This is where the paths of the two pendulums separate. Had an idea how the complexity of this motion might be visualized. He suggested a strategy that records only particular moments, rather than the complete process. For example, one can always capture the situation where the double pendulum goes through the stretched configuration with a positive angular velocity of the outer pendulum. Like now, now, and now. At such moments, the angle phi1 of the inner pendulum and its corresponding angular momentum should be measured, and one plotted versus the other. In this way, one will obtain a point of the so-called phase plane of the inner pendulum. While the motion progresses, one waits for the return of such stretched configurations and records them in the phase plane point by point. While the corresponding angular momentum is a less regular type of motion. This can already be seen in the bottom left trace. The first few points have been generated, the outer pendulum changes its direction of rotation, and for a while it passes the stretched configuration at negative angular velocities only. There are therefore no points in the Poincaré section. Only now do we see the reappearance of points. In contrast to the previous cases, however, they are not confined to a line, but are distributed over an area which in the long run they will fill densely. This type of motion is called chaotic. The points in the Poincaré section fill up a so-called chaotic band. We calculate 300 successive points for each of a number of further initial conditions, and finally obtain this picture. The Poincaré sections give an indication of the rich complexity of the dynamics of a double pendulum of this sort. They condense in one picture the long-term behavior of a large number of trajectories in a way that the eye can easily follow. They show how closely interwoven at one and the same energy value regular and chaotic behavior can be. A small change in the initial condition, and the features of the eventual trace may be quite different. Under such circumstances, long-term prognosis becomes practically impossible. The system's behavior is in certain respects unpredictable, although of course it is strictly determined by the equations of motion. In order to get an overall view, let us now consider the Poincaré sections at 12 different energy levels. Let us begin with the low energy point 5. The white line encircles the phase plane area that is accessible at this energy. The Poincaré section consists essentially of lines. It contains two major resonances which correspond to the two oscillating eigenmodes. At the central resonance, the two pendulums oscillate out of phase. Right at the top of the Poincaré section is the resonance that corresponds to the second eigenmode. Both pendulums oscillate in phase here. The resonance we are now following can be viewed as a combination of the two eigenmodes. The line structure of this picture reflects the regularity of the motions of this low energy. When the energy is doubled, some of these lines have broken up into chains of islands. At the energy 1.5, chaos is clearly visible. The central resonance has split into two resonances. Chaos begins to dominate, and little room is left for the islands of order. It is interesting to see how the central resonance has developed after the bifurcation. We first observe the trace of the left-hand resonance. It has the shape of an ellipse and evolves in a clockwise manner. images of one another under time reversal. At energy 4, we find nothing but chaos. As the energy is raised further, order emerges again from the chaos, at first in the form of the central resonance that we are now going to observe. The outer pendulum completes the rotation at exactly the same frequency at which the inner one oscillates. At further increasing energy, the ordered area seems to shrink again. But regular motion finally takes hold and also appears at other places in the phase plane. As for instance, around this resonance, which consists of 2 points in the Poincaré section, here we show the course of the corresponding motion. At energy 10, we find for the first time that a line crosses all through the phase plane and divides the chaos into 2 parts, an upper and a lower one, between which the motion can no longer deviate, even on a long-term basis. As energy is increased still further, more and more of these continuous lines appear, and the motion becomes more and more regular. Let us see what main resonances occur at high energies. We have already encountered the red resonance, so let us focus on some of the others. At this resonance, the outer pendulum oscillates exactly once, while the inner pendulum completes 1 rotation. This is the time-reflected version of the resonance we have just seen. The traces are identical, but the motion progresses in opposite directions. We find another resonance hidden in a chaotic band. Here the 2 pendulums rotate in synchrony, the inner clockwise, the outer counterclockwise. At energy rising to infinity, or at vanishing gravity, the chaos disappears completely. The angular momentum becomes a conserved quantity, and the motion proceeds on lines that lie parallel to the phi-1 axis. We describe it by noting how much to the right or left the points on the ordinate are displaced in one step of the Poincaré process. This is shown by the white lines that cross this picture. Let us follow the motion for some typical starting points that we pick on the ordinate. In the upper yellow area, the inner pendulum rotates counterclockwise while the outer one oscillates. In the blue area, both pendulums rotate counterclockwise. Note how from point to point the angle phi-1 always increases by the same amount. This starting point is so chosen that the inner pendulum does not rotate but only oscillates while the outer one rotates. elements rotate counter to one another, so that the total angular momentum is small. Finally, in the orange colored area, the motion up to time reversal is the same as in the yellow area. Let us quickly recall the Poincare sections as energy increases. At first, order dominated in the form of quasi-periodic motions. Then, chaos spread and finally covered the whole phase plane. Then, islands of ordered motion re-emerged. And here, at energy 10, a green belt appeared for the first time, crossing the phase plane. In a little while, we shall look at this boundary between two chaotic domains in greater detail. But first, let us go on raising the energy. More and more separating lines appear, called KAM lines for short, after the mathematicians Kolmogorov, Arnold, and Moser, who proved their existence. The final Poincare section is composed of such KAM lines only. From here on, we are going to move backwards to follow the scenario of the decay of order as energy decreases. We know that one of the KAM lines will be the last to survive. Let's therefore look at this section of the green area in close-up. The first thing we do is to look at the most important resonances. For this initial condition, the angle phi2 rotates exactly twice as fast as phi1. For this initial condition, the ratio of the angular velocities is exactly 1 to 3. This resonance is therefore characterized by 3 points. Between the two resonances just shown, there lies a resonance of 5 points with a ratio of the angular velocities of 2 to 5. This ratio is called the winding number. Resonances always have rational winding numbers, while quasi-periodic motions have irrational winding numbers. Between the resonances with winding numbers 1 to 3 and 2 to 5, there lies another one with a winding number of 3 to 8. We begin to realize a simple algorithm. The two last winding numbers give us the next one by simply adding numerator to numerator and denominator to denominator. This resonance has accordingly the winding number 5 to 13, the next one 8 to 21, and so on. The numbers rapidly approach a particular irrational number, the golden ratio. As we shall see, this irrational winding number characterizes the quasi-periodic motion whose KAM line keeps chaos in check longest as energy is reduced. At energy 20, the resonances just described appear as conspicuous chains of islands, with green KAM lines and chaotic bands beside them. At energy 10, the resonances are still clearly visible, while the chaotic bands have spread and are now confined by one line only, namely the last KAM line. Let us pick a starting point on this KAM line and observe the last stable quasi-periodic motion in the middle of chaos.
好，下一个我们稍微停一下，这个实际上刚才看到这个事情我并没有讲，这是个保守系统。不过这里头碰见的一些东西我们提到了，比方说准周期的运动在高维空间里是在一个环面上，潘克莱截面截出来以后是一个圈儿，这种东西在保守系统里是很多的。而且呢，如果在某一个地方有的话，一个圈儿一个圈儿一个圈儿，这些东西你可以看得到。如果用这种做法，你有看不见的，就是在每2个圈之间有一个不稳定的双曲点，你可以打个叉，它的数是一样多的，一个圈一个叉，一个圈一个叉的转过来的。然后呢，在走向混沌的过程中间，这些圈逐渐的破坏，最后破坏的那个是转数，是无理数。哪个无理数呢？黄金比。刚才说了一下这个事儿，这个里头他没用 Ferri 求和，但是那个序列是斐波那契，他的办法也是用 Ferri 求和的办法得到的。我看不休息了，因为底下不是很长，人也不很多。底下这个接着演的这个呢，就是化学震荡反应的一小段历史。它是一个俄国的电影，待会儿字幕里还会出一点俄文，但是德国人把它翻成英文了，所以大家就直接看吧。这个它的题目呢，俄文叫做“尼卡格达尼高维利尼卡格达”，准确的英文就是 “Never say never”。怎么变成全屏啊？
那个您把它暂停掉了。
哦，暂停了。
到那个。
哦，要拖到这个地方来。对。
42分。
对，停一下看看。哎，还可以再往前拖一点。对，好。全屏，好。
Never say never. This is the story of a discovery. There are several chapters in this story, which began in 1950. This is the first. A chemical compound was being analyzed in the laboratory. It oxidized and changed color as was expected. Suddenly the researchers saw that the oxidized compound had spontaneously undergone reduction, after which the reaction proceeded as before and again reversed. Boris Gills, the researcher, was no newcomer to science. He immediately understood that what he had seen was incredible.
这是第一次看到化学震荡，贝劳乌索夫。
After analyzing the reaction for several months, he concluded that this was a phenomenon as yet unknown to science. A periodic, long-term, pulsating reaction has been discovered never previously described, said his report to a chemical journal. The reply dismissed his suggested that this may be due to oscillating chemical reaction. But this hypothesis was rejected as invoking a phenomenon impossible in nature. Nevertheless, what dictates the pulsating rhythm of this slime mold as it grows on a rotting stump?
slime mold 黏菌。
The heart of a frog contracts and relaxes uniformly. What helps it to keep its beat?
狗心。
The mystery of such rhythm is the mystery of the processes controlling life itself. Now we turn to a new chapter in our story. The town of Pushchino near Moscow, the Institute of Biological Physics of the USSR Academy of Sciences. 15 years after the chemist Belousov observed his bizarre oscillations, two budding scientists started working here. Henryk Ivanitsky, a graduate of a technical college, who later became interested in the automation of biological research, and Valentin Krinsky, a graduate of the Moscow Physico-Technical Institute. Their research project was concerned with certain unusual modes of cardiac activity. To begin with, as is usual in physics, they translated their problem into the language of equations and constructed a mathematical model. The heart was represented as a set of large number of points with definite properties. In order to make this seem less abstract, we'll attempt to show the properties of such a point. Here is a burner filled with viscous oil, which rises slowly along the asbestos wick. When the wick is soaked, it burns, but not for long, since the oil burns out faster than it rises.
灯芯太细，供油不足。
The wick will not burn, for the fuel has not yet risen. Now the wick has sufficient energy and the flame will catch. Then the process starts all over again. If we line up several such wicks in a row, the excitation will progress from wick to wick, or from point to point, in the language of mathematics. As the flame progresses, it leaves behind a zone temporarily incapable of burning. But at the end of the zone, the wicks have been saturated again, and they can be lighted one after another. This is a model of what theorists call an active or excitable medium. If such elementary units are distributed on the plane, we observe an interesting effect, regular waves. It is such a medium that mathematicians liken to a heart, also consisting of a multitude of standard elements, that is, excitable cells.
这是那个老计算机的卡片儿。
A computer was programmed to research the mathematical model.
老打印机。
It reported that if there is a center of excitation in an active medium, circular waves will issue from it. such sources could be found in the heart muscle. Could there be a mistake in the mathematical model? The next third chapter with the words, at that same time and in another place. University summer seminars are held here at the bio station on the White Sea. A favorite saying here is never say never. In other words, never reject anything without checking it out first, even the most fantastic hypotheses. Circulation, and not widely known to chemists. It was Schnell who had convinced Belarus of the publishing.
这是1958年贝尔乌斯克唯一发表的放射医学杂志，没什么人看的报告。
Regular seminars on oscillating processes. The subject was becoming a major one in biology. Finally, success. A discovery of something that Belousov's opponents never suspected existed. They found that the reaction was not like a match that burns only once, but like a wick, capable of being lighted again and again, with the sole difference that the wick is fed by oil. But here, energy stored in the substance itself is utilized cycle after cycle. The solution behaved like an elementary point in an excitable medium. This prompted the lucky idea of distributing it in a thin layer over a flat surface. It seems the picture drawn by the computer in its research of a theoretically active medium has come to light. But that was a speculative diagram, while this is reality. What was most surprising was that the solution produced its own sources of excitation. The medium itself produced a spark, from which issued self-sustaining waves, or as they would soon be named, auto waves. These waves caused synchronized changes in millions of molecules, creating a distinct pattern of moving rings. At the request of the authors of the mathematical model, the homogeneity of the solution in a small sector was upset, and the circular order wave was indeed disrupted and spirals started forming. The spirals multiplied, producing ever new centers of excitation. The identity of the mathematical forecast and the experimental picture was astounding. But nature is a single whole, and it is doubtful that auto waves exist only in chemistry. The Institute continued its search of unusual sources of excitation in the heart tissue. By this time, the scientists had designed special
这是个心脏肌肉切出来的一片心肌。老磁带机。
Direction of camera, Yevgeny Pokrov.
演完了。好，说几句话咱们就完全结束了。最后的这个片子里头有一个概念非常重要，这个不是我这次讲课所提到的，但是呢，在整个的非线性科学里头非常重要的实际效果、实际影响很大的领域，就叫做继发介质，可继发的 excitable media。那么这里头给的最简单的例子，我不知道大家看明白了没有？你底下有一个油的供应，比方一个油的浅浅的槽，然后你架上一个支架，放很多个灯芯在上头，每一个灯芯都不够粗，所以它吸上来的油把它点着以后只能点一会儿，底下就供应不足，就得灭掉了。但是把这样的东西呢布成一个阵，那么这一个点着了的自己快灭了的时候，可以把邻居点着，邻居把下一个点着，就这样的一个非常简单的一个实验的设备，可以形成波浪往上传，然后这种波浪传过去以后，有的时候可以往回传，是因为原来灭掉的它又已经油又充分了。而这个呢，可以是在自然界的森林火灾的模型，只不过空间时间的尺度都变了很多倍。这一大片的森林是一个能量的源泉，着起来以后，这段烧过了，在一个短时期之内当然不能再烧了，但是几十年之后森林长起来了，自然的这个过程它又会重复，所以它里头长了心脏啊，讲了所有这些东西。那么这些一个能够有继发的，最早是在化学介质里头，是从贝洛乌索夫50年代的观察开始的。那么最后的镜头是1980年，当时的苏联给了这几个人列宁奖金。这列宁奖金最早叫斯大林奖金，后来改成列宁奖金，它也是只给活人不给死人的。但是这一次是例外，贝洛乌索夫已经不在了，但是这个奖金不能不提到他，是他的工作开始的，所以这个片子也是从贝洛乌索夫开始，贝洛乌索夫接书下来的。那么这个人是一个沙俄时代1917年之前受了高等教育的，在50年代已经年纪很大的一位化学教授，是吧？所以这里的教训是 never say never。他的稿子送出去的时候，编辑里头提到了，主编的反应是说化学里从来没有这样的事儿，所以他的主要的文章都给拒绝了，最后找了一个很不起眼的小杂志，在58年留了那么一篇记录下来。这种激活介质的问题，在90年代，我跟郑伟模在上海科技教育出版社组织了一套非线性科学丛书，在整个的90年代，这个丛书出了30本，每一个丛书一个专题。按我们最早的计划是有一本书写这件事的，那是在80年代后期90年代初，在国内做这件事情做的最多的人就是上海生化所的丁达夫，他答应写这本书。但是后来我们的研究工作更多的是被经费的指挥棒所指挥着，丁达夫所待的是上海生化所，所以他就把注意力转向了给钱的蛋白质研究了。于是乎这本书就一直欠到那儿，最后也没有出来。所以大家要看的话呢，得去找英文书，中文的像现在我不知道有人认真写过没有啊。最后我说几句话来结束我整个这几讲。我讲的主要问题是毫散系统。今天的第二个例子，双摆或者是负摆是保守系统。但是符号动力学的概念是不受这个限制的，就是不管你的自由度多还是少，不管你是毫散还是保守，符号动力学是个非常一般的概念。所以我想把最普遍的符号动力学在这给大家描写几句。如果你的动力学发生在一个相空间，这个相空间可以是高维的，但是它是一个紧致的相空间，用数学概念，紧致的 compact。 什么叫做紧致空间？紧致空间就是可以用有限个 覆盖有限块东西把它盖起来的。比方说一个球面是一个紧致空间，是因为你一共需要剪2张报纸，一个从上头往下包，一个从底下往上包，它们可以有一些交界重叠，你就可以把球面全部做了。但是一个无穷的平面不是紧致的，你不可能用有限个这样的东西把它包起来，除非你做一些投影，把无穷圆点投影到一起等等，做到了那种放射空间里。所以一般我们讨论一个紧致的空间，它可以由有限个覆盖把它盖起来。你给每一个覆盖用一个字母起一个名字，然后你的运动无论怎么运动，在你的这个空间里走，所以它就在不同的覆盖之间来回跳，把它的轨道换成这些覆盖的名字，你就得到了一个很自然的符号动力学。但是这样的符号动力学能不能有很丰富的内容，这就看你的具体问题了。我们所讨论过的所谓实用符号动力学是有非常多的内容的，那是因为我们把它限制到了比较具体的问题上了。1维的迭代，2维的我非常简单提了一下，高维的微分方程更简单的说了几句，但是它们有一个共同特点，就是它们只有一个正的列布诺夫数，只有一个方向是不稳定的。这种东西如果只发生在一个点无所谓，单摆都有这样的不稳定点，但是如果在相空间里有一片点是连起来的，这些点都具有这样的处处不稳定的性质，你就导致了混沌运动了。那么这种由一个不稳定方向一个正列布诺夫指数决定的混沌，是到现在为止研究的最多的。有人把有2个列布诺夫指数正的这样的混沌叫做 hyperchaos 超混沌。不过你要去看的话， hyperchaos 的理论结果就相当之少了，非常多的数值结果在比较高维的有比较多的不稳定方向的混沌里头。所以这方面真正做的比较透彻的工作到现在为止还限于一个正列布诺夫指数的系统，维数可以不是1维，比方说罗伦斯方程是3维，但是它是一个正列布诺夫指数的系统。所以这里头呢，最主要的一条就是复杂性是和特殊性一个方向的。当你对你研究的问题做加上条件限制的比较特殊以后，你的研究可以很具体，得到很多结论，看到很多复杂现象。但是如果你企图用一般语言去研究复杂性的话，你走不了很远，是吧？那么这件事情是我奉劝各位今后注意的。在我们这个以清谈为传统的国家里，随便的谈论系统科学复杂性，准备用一些普遍性的词儿就把什么理论都建立起来，这样的人大有人在。而我不奉劝大家走这么一条道路，是吧？很多人说中国是整体论的 holism， 说外国人是这种 reductionism， 就是把什么都分解下来的，说我们的观点优于他们等等。你们不要相信这种东西。在最早的人类刚从这种刚开始有点文化的时候，不可能对周围的世界有细致的认识，因此各个民族的早期思想都是整体性的。但是东西方文化发生了很严重的一次分叉，现在我就可以用这个点了， bifurcation point， 有一次分叉。这次分叉从历史上讲发生在公元前第3世纪，就是公元前299年到公元前200年，这个第3世纪。2件事情使这个东西方文化从此2000多年走上了不穷的道路。公元前290年，马其顿帝国的大帝托勒密一世下命令，在现在的埃及的亚历山大港建立一个大的图书馆， 就是有名的亚历山大图书馆。它建立的时候藏书7000卷，真正是卷，是埃及的纸草纸写的卷起来的这种东西。它后来几百年后毁掉的时候，它已经有100万卷藏书。世界各个地方，当时它的大帝国的范围之内，地中海的沿岸、非洲北部、阿拉伯世界、欧洲南部，学者们被邀请到那儿去进行研究。欧几里得在这儿写的他的欧几里得学、几何学。如果大家看一下欧几里得比较完整的名字，在西方的科学史上叫做 Euclid de Alexandria， 亚历山大的欧几里得。所以他不是希腊的，他在希腊对面的亚历山大，是吧？那么这件阿基米德的原理，阿基米德也在这儿工作过。很多欧洲早期的自然科学的开创者都在亚历山大图书馆工作过。这是发生在欧洲的一件事情。公元前3世纪，公元前3世纪的最初的几十年，就是290年、28几、27几年，还是我们诸子百家的后期，像荀子、像墨子，大概都活到了这个时期，就是他们死在公元前第3世纪，所以那个还是诸子百家、百家争鸣的时代。公元前221年，秦始皇统一中国。公元前213年，发生了一件事情，就是秦始皇下令焚书，把天下所有的书都烧掉，只有皇宫里保存一套。可惜这一套被项羽把咸阳打下来的时候给烧掉了。下这个命令的时候说，有一些书不烧，就是医药、种树还有算卦问卜的书不烧，是吧？不过鲁迅已经说过，秦始皇说不烧的书后来都找不到了。废私学，不过那个时候没有公家的学校，就是一些知识分子开的私塾。秦始皇在213年的命令是废掉私塾，今后谁要学认字儿的话，要以吏为师。这大家查历史，就是以那些官们为师。可见学字儿的主要目的就是为了做小官，从小官做大官。从以吏为师到后来的学而优则仕，到今天从海外回来的哪一个年轻人工作的好一点，干脆赶紧给他封各种官衔儿。这是2200多年一脉相承的中国文化传统。这个发生在公元前213年。公元前212年，秦始皇下令在骊山后头的地方挖了个坑，把460多个当时的高级知识分子放在坑里埋了。这两件事情都发生在公元前3世纪。西方有他的一个科学研究的传统，有一些人毕生献身科学。有1600年被烧死的布鲁诺，中国有过比较大的作为个人讲是科学家，像东汉的张衡。但是你们看一下，他首先是一个官吏，一个相当有地位的，但是他有自然科学的能力，有这方面的兴趣，有所创造。但是我们历史上缺乏献身科学的这样的人物，所以在这个意义上讲，我们这个传统到今天这个差别，大家应当感觉到。所以我劝大家，只要你是献身自然科学的，对于把世界分析、分解、进行真正具体研究，对这种事情做了贡献很少的中国人，没有多大的权利谈整体的等等。所以呢，如果谁要说易经等等就去研究，要想解决今天的问题之类的，我劝你们不去参与这些事儿。这么大国家有几个人愿意研究，他就去研究好了。不要以为现代科学的答案在老祖宗的这些书里就有，有个别一些人愿意当做自己的专业去研究，是好的，可以做去，我们也不反对，是吧？对于这些东西，我想还是马克思的话。马克思在评述希腊神话的时候说过，希腊神话是人类幼年时期的天才创造， 易经之类的也是中国这个民族在自己的文化幼年时期的一些创造。不要希望从这些东西里得到现代科学的答案，大家还是老老实实、扎扎实实研究具体问题、具体系统。好，我想整个的这个课就到这儿结束。谢谢最后这几位坚持到现在。今天在教室里的人数大概是开始的人数的1/10吧，这个也好。我也说过，只有一个人讲，一个人听我就愿意讲。行，再见。